What happens if you fall into a black hole? Would you stretch into infinity? Would you vanish completely? Or would something stranger happen? Something that no scientist, no telescope, no equation can fully predict. Tonight, we're going to follow that question slowly, patiently, and fearlessly, all the way to the edge of the unknown. You might imagine a black hole as a kind of cosmic monster hiding in the dark, waiting to swallow stars, light, and time itself. And in a way, you're not wrong. But that picture is also incomplete, because black holes aren't just dangerous, they're fundamental. They're not just the end of something, they're often the beginning of understanding what happens when the rules of the universe stop playing by our expectations. They're not monsters, they're puzzles made of gravity. They're the places where our best science meets its limits. But before we dive into the center of a black hole, we need to ask, how does one even form? Because black holes are not born in silence. They are born in collapse. Imagine a star far bigger than our sun reaching the end of its life. For millions of years, this massive star has been fighting a battle between gravity pulling inward and nuclear fusion pushing outward. But when it runs out of fuel, fusion stops, and gravity wins. The core begins to collapse, shrinking faster and faster until, in a fraction of a second, the entire star implodes. What's left is no longer a star, it's something else entirely. A place in space where matter has been crushed so completely that it no longer takes up space in the normal way. A place where gravity becomes so strong that nothing, not even light, can escape. And that's what gives black holes their name. They are black not because they are dark in color, but because they do not let light out. They're not glowing. They're not reflecting. They're just gone, like a hole punched in the fabric of everything. But wait, is there really a hole there? Is it empty space? Or is something still inside? Before we answer that, I'd love to know something. Where in the world are you watching from tonight? Tell me your city, your country, your little corner of the universe, and drop it in the comments below. And if you're enjoying this slow and curious journey into the impossible, it would mean a lot if you'd consider subscribing. It helps this quiet space find others who might need a moment of wonder tonight. Now, let's go deeper. The edge of a black hole is called the event horizon, and once something crosses it, there's no turning back. Not for a rocket, not for a beam of light, not even for time as we understand it. But here's the strangest part. From the outside, to a distant observer, nothing ever actually crosses the event horizon. If you were watching a spaceship fall into a black hole, you'd see it slow down, dim, and freeze right at the edge. It would appear suspended there forever. But from the spaceship's point of view, the story is very different. Inside the ship, time flows normally. The event horizon is not a wall. It's not even visible. You cross it without noticing, and then the real journey begins. Gravity begins to intensify. Space stretches in bizarre ways, and everything starts to pull toward one central point: the singularity. That's the heart of a black hole, a place where all the mass has collapsed into a single, infinitely small point. At least that's what general relativity predicts. But even Einstein's brilliant equations can't fully describe what happens there, because once you reach the singularity, the math breaks down. Time, space, gravity, they all become unrecognizable, and this is where the mystery really begins. What is the singularity made of? Does it exist at all? Or is it just a placeholder for something we haven't yet discovered? Some physicists believe singularities are real. Others think quantum mechanics will someday explain them away. But one thing is certain: once you fall in, you can't avoid it. The singularity is your future, just like tomorrow is your future right now. Except you'll never get to tomorrow, because as gravity pulls you inward, time starts to stretch, distort, fold, until it doesn't make sense anymore. So what does it feel like to fall into a black hole? Let's imagine, not in fear, but with quiet curiosity. You're in a spaceship, alone, floating peacefully near a black hole, not too close, not too far. From your window, it doesn't look like much. There's no swirling storm, no flashing lights, just a patch of sky so dark it's unsettling. A perfect circle where the stars behind it have disappeared. You check your readings. You're approaching the event horizon, the invisible threshold. There's no bump, no jolt, no sound. But suddenly, your instruments begin acting strangely. The clock on your dashboard ticks normally, but a second ship, one staying behind to observe, sends you video footage, and in that video, your ship is slowing down. Your movements look sluggish, as if time itself is thickening around you. To them, you are frozen just above the event horizon. But to you, everything feels normal. This is where things become strange. You cross the event horizon, smoothly, silently, and now you're on the inside. You're past the point of no return. Behind you, nothing can escape, not even light. Ahead of you, the pull is relentless. But it's not a simple pull like gravity on Earth. Here, it's a gradient. The difference in gravitational force between your head and your feet becomes extreme. If the black hole is small, that difference, called tidal gravity, becomes deadly fast. Your body begins to stretch. Not violently, not all at once, but relentlessly. Your feet are pulled faster than your head. Your spine elongates. This process has a name: spaghettification. It sounds almost comical, but it's real physics. You don't feel pain. You feel pulled into a line. Your atoms themselves begin to line up. If the black hole is supermassive, like the kind at the center of galaxies, the tidal forces are gentler at the horizon. You might cross it without noticing. You might even have time to think, to breathe, to record what you see. But even then, the end is certain. Space is not a backdrop here. It's twisted. It's not pulling you toward the center. It's falling with you. Imagine standing on a waterfall made of space, and the riverbed itself is tilted inward. You're not moving through space. Space is moving through you. It's falling toward the singularity, and you're riding the current. There's no turning back, not because of momentum, but because the structure of space-time doesn't allow it. Inside a black hole, all paths point to the singularity. Not just in space, but in time. Going forward in time means getting closer to that center. The singularity isn't just a place, it's your future. You can't avoid it any more than you can avoid tomorrow. You don't fall into the singularity, you fall toward it, through dimensions you can no longer recognize. Your measurements no longer work. Your compass spins. Your clock ticks strangely. Light curves. Angles collapse. And space begins to lose its shape. Some physicists believe that before you reach the singularity, the known laws of physics dissolve. Quantum effects, usually tiny, may suddenly dominate. Particles behave unpredictably. The certainty of mass, energy, and identity starts to blur. What are you now? Still a person? Still a ship? Or have your particles become information, stretched across the horizon like code written in gravity itself? This leads to a question that still shakes modern physics. Is the information lost forever? According to general relativity, everything that falls into a black hole is gone. Erased, deleted, absorbed without a trace. But according to quantum mechanics, that's impossible. Information can't be destroyed. It can be scrambled, it can be hidden, but not lost. So who's right? That question has haunted physicists for decades. It's called the black hole information paradox, and it suggests that black holes might not be the dead ends we once thought. Some theories say that information is stored on the surface of the event horizon, a kind of holographic imprint. Others suggest that black holes don't erase information, but rewrote it, or that Hawking radiation, a faint trickle of quantum particles escaping the black hole, may carry the information back out, piece by piece, over billions of years. But none of these answers are complete. We're still searching, still guessing, still wondering what really happens inside. And that's where the beauty lies. A black hole is not just the end of a journey, it's a doorway, a crack in the foundation of reality, a reminder that even our best theories have edges, and beyond those edges, mystery lives. Now, let's drift closer. We're not at the singularity yet, but we're feeling the pull. The rules of the universe are trembling, and somewhere ahead of us, past equations and edges, is something we don't have words for yet. What happens beyond the edge of understanding? That's where we are now, hovering just above the singularity, in a place where the usual concepts begin to fail and the mind begins to stretch, just as space did. Inside this black hole, time no longer flows like a river. It collapses inward like everything else. You no longer move through time. You fall into it. The singularity is not ahead of you in distance, but ahead of you in time. There's no path you can take that leads away from it. Every second carries you closer. Every breath, if breath could exist here, is another tick toward the center. But what is that center? Is it a real place, or just a mathematical limit that we can never actually reach? Some physicists believe the singularity is infinitely dense, a point where mass has no size and gravity has no bounds. But others wonder if our equations are simply breaking under the weight of their own assumptions. General relativity, Einstein's masterpiece, tells us space and time curve under the influence of mass. But at the singularity, the curve becomes infinite. That doesn't mean we've found truth. It might mean we've found the limits of our math. Quantum theory, which governs the small and strange behavior of particles, should take over here. But the two theories don't agree. They speak different languages. One talks about smooth curves and elegant geometry. The other speaks in sudden jumps and uncertain positions. Trying to combine them is like trying to overlay music onto a blueprint. They're both real, both beautiful, but they don't yet harmonize. This is why the singularity matters. It's not just the end of a star, it's the end of our agreement about how the universe works. It's a spotlight on the cracks in our knowledge. And in those cracks, strange possibilities appear. One of those possibilities is the idea of a Planck star, a theoretical object so small and dense that quantum pressure stops it from collapsing into a true singularity. Imagine gravity pulling inward while quantum forces push outward. Somewhere in between, a balance is struck. The star doesn't disappear, it just becomes unreachable, sealed inside its own gravity. Another idea, that the singularity might not be the end, but a transition, a kind of wormhole, a bridge to another place, another time, another universe entirely. Some solutions to Einstein's equations actually allow for this. They suggest that black holes could be tunnels, and that on the other side is something new, a white hole, a place that can only expel matter, not absorb it, a cosmic fountain instead of a drain. No one's seen one. No one's proven they exist, but in the mathematics, they're possible. And in the imagination, they're powerful. Because if black holes are tunnels, then falling into one might not mean destruction. It might mean transformation. Maybe information isn't lost. Maybe it's carried. Maybe what you were, as atoms, as patterns, as data, is reshaped on the other side. But then the question becomes, how could anyone ever know? We can't see inside a black hole. We can't send a signal out. The event horizon traps not just light, but certainty. That's what makes black holes so unnerving. They are places in the universe where the future becomes undefined, not because it doesn't exist, but because we can't know it, not even in principle, and yet somehow they still affect us. The gravity of a black hole reaches far beyond its edges. It curves the paths of stars. It bends light. It keeps galaxies spinning. At the heart of nearly every large galaxy, including our own Milky Way, is a supermassive black hole. Millions, sometimes billions, of times more massive than the Sun. They sit quietly in the center, not devouring everything in sight, but holding entire structures together. Without them, the stars would drift. The galaxy would unravel. So even though we can't see them directly, black holes shape the visible universe. Their shadows, their influences, their silent orbits, all of it reminds us that the unseen is just as real. In 2019, for the first time in history, we saw the outline of a black hole. Not the hole itself, but its shadow, a glowing ring of hot gas swirling around the event horizon, captured by a global network of telescopes called the Event Horizon Telescope. It was the galaxy M87 55 million light-years away, and in the center of that orange halo was darkness, perfect, complete, unbroken. A silence at the heart of flame. That image wasn't just a photograph, it was a message, a confirmation. The impossible shape was real. We had never touched it, but we had felt it pull on light itself. You're still falling. The singularity is still ahead, and somewhere inside this fall, you begin to wonder, what if there's no end? What if inside? This black hole is a different kind of space entirely, not empty, not nothing, but full of something we don't yet have the tools to describe. What if the singularity isn't a point at all, but a process? What if the black hole isn't a dead end, but the beginning of a different kind of physics? A physics that sees space and time not as separate threads, but as woven fabric. A physics that doesn't end in infinity, but loops, folds, rewrites. These questions aren't science fiction. They're what happens when real equations meet real limits. They're the questions left behind when stars collapse and math runs out of breath. And the deeper we fall, the more we realize. Maybe it's not about answers. Maybe it's about continuing to ask, even when the sky turns black. By now, we've accepted that black holes are more than objects. They're boundaries. Boundaries between what we know and what we can only imagine. But what if the boundary isn't just at the event horizon? What if every black hole is also a boundary in time? A frozen moment where the universe keeps its deepest secrets folded away. Think of it this way. A black hole doesn't just trap light, it traps stories. The story of the star that formed it, the story of every planet, asteroid, or drifting particle that fell in. The story of time itself bending to the will of gravity, and yet, from far away, all you see is the shape, not the history. Physicists believe that everything a black hole consumes affects its mass, its spin, and its charge. These are called its conserved properties, the only things left behind after the fall. Everything else disappears, or so it seems. But that idea creates a paradox. If two completely different objects, say a planet and a spaceship, fall into a black hole, and the only thing that changes is the mass, spin, and charge, then from the outside, those two events look exactly the same. The details are gone. The distinction is erased. But this breaks one of the core principles of quantum mechanics. Information must be conserved. No matter what happens, the universe isn't supposed to delete the details. It can hide them, scramble them, stretch them into patterns too complex for us to decode. But it cannot simply forget. So now we're left with a tension, a disagreement between general relativity, which predicts information loss, and quantum theory, which insists on memory. And this tension is not just theoretical, it sits at the very heart of physics. It's the thread we keep pulling, hoping the universe will unravel just enough to show us what lies beneath. Stephen Hawking, the physicist most famously associated with black holes, once believed that information was lost. But later in life, he changed his mind. In the 1970s, he discovered something extraordinary, that black holes aren't entirely black. Thanks to quantum fluctuations at the event horizon, black holes slowly emit faint particles, a process now known as Hawking radiation. Over time, this radiation causes black holes to evaporate, slowly, quietly, over trillions of years. But here's the mystery. Hawking radiation appears to be random. It doesn't seem to carry any of the information about what fell into the black hole. It's like steam rising from a kettle. You can't tell what kind of tea was inside. If that's true, the information is lost. But if that's false, then somehow the radiation must be encoded. Subtly, faintly, carrying the fingerprints of everything that ever crossed the horizon. Some physicists believe that the information is scrambled on the event horizon itself, like a giant gravitational hard drive, storing data in unimaginable density. This is known as the holographic principle, the idea that everything inside the black hole is projected onto its surface, like a three-dimensional world compressed into a two-dimensional shell. It's a radical concept, but one that has gained serious traction. If true, it means the universe is even stranger than we thought, a place where volume and surface are deeply connected, where inside and outside are just perspectives. But even if information isn't lost, we still don't know where it goes, or how we could ever retrieve it. Imagine trying to reconstruct an encyclopedia from ashes floating on the wind. Theoretically possible, practically impossible. Yet science continues to search because this question, where does the information go, is more than academic. It speaks to the nature of reality, to whether the universe forgets, or whether somewhere in the deep geometry of space-time, everything is still written. Now, let's go deeper still. Because if black holes evaporate through Hawking radiation, that means they don't live forever. They shrink slowly until one day they're gone. But what happens in those final moments? Is the information released in a final flash, a grand finale of data returning to the cosmos? Or does something else happen? Some theorists suggest that as the black hole shrinks, it might leave behind a Planck-scale remnant, a tiny, stable core that holds the information, locked away in quantum code. Others believe the information is smeared across the radiation, encoded so subtly that only a future physics will know how to read it. But there's another possibility, one that feels almost poetic, that black holes are not the end of information, but the keepers of it, that everything they swallow becomes part of the cosmic archive, not lost, just waiting. Waiting for new equations, new eyes, new understanding, because maybe the universe doesn't forget. Maybe it remembers in silence, in gravity, in light that bends just slightly more than we expected. Maybe every black hole is a library, locked, sealed, but still standing. And maybe someday we'll learn how to open the door. Let's return now to the moment of crossing, that invisible boundary, the event horizon, where everything changes but nothing announces itself. There is no alarm, no burst of light, no ripple that says you've entered the black hole. From your perspective, you pass the threshold like walking through air, but from the outside, from the universe you left behind, you seem frozen in time, suspended at the very edge. This contradiction is not just philosophical, it's built into the structure of space-time itself. And it raises one of the strangest questions of all. Are you inside the black hole, or still outside from someone else's point of view? In general relativity, both perspectives are valid. You are falling in, and you are stuck at the surface. Time and space bend to match the motion of the observer. This is more than an odd feature of theory. It's a sign that reality, at its most fundamental, might not be a single narrative. It might be multiple layers of truth, overlapping and coexisting, each one consistent within its own frame, but wildly different from another. You experience one story, the fall. Someone else watching from afar experiences another, the freeze. And both are correct. This idea that reality can hold multiple, seemingly contradictory truths is at the core of what makes black holes so hard to grasp. They challenge our demand for a single, shared perspective. They suggest the universe is less like a single painting and more like a gallery full of mirrors, each showing a different angle of the same strange shape. And nowhere is that shape more twisted than at the singularity. As we fall closer, the rules continue to melt. Not just time and space, but mass and energy begin to blur. It's possible, some physicists believe, that the interior of a black hole doesn't even behave like a place anymore. That distance becomes meaningless, that objects falling in from different directions are funneled into the same final line, not because they moved there, but because that's where all futures inside a black hole lead. There are no alternate routes, no forks in the road, just one arrow, one conclusion, one inevitability, the singularity. But again, is it a point or is it something else? Our equations offer both possibilities and contradictions. Some researchers suggest that the singularity might not exist in the traditional sense at all, that instead of an infinite point of density, the collapse is halted by quantum gravity. Effects we haven't discovered yet. In these models, space-time doesn't rip, it rebounds. And in that rebound, a new region of the universe might form. This is the basis of the black hole to white hole transition model. An idea that suggests that black holes don't end with erasure, but with explosion. Over unimaginable lengths of time, a black hole might transform, releasing everything it once held in a final eruption, not randomly, but precisely as if time had reversed and the fall were now a rise. This would solve the information paradox. It would preserve the symmetry of physics. But it also implies something even stranger, that inside every black hole is the seed of something else. Not death, but rebirth. Not deletion, but recursion. A cosmic loop playing out over billions of years, the universe folding in and blooming out. But this model, like all others, remains unproven. We don't have the tools yet to peer inside. We can only infer, model, imagine. But imagination, grounded in math, is how physics grows. And so we keep asking, what if the singularity is not a destination, but a transformation? What if, as we fall inward, our concept of self dissolves just like time and space, not destroyed, but reassembled in a different form? Could identity survive such a journey? Could information, memory, or pattern persist? Some theorists believe that consciousness, if reduced to information, could be preserved, transformed but not extinguished. That what you are at the level of neurons and atoms could be encoded, not as a soul, not as awareness, but as structure. And structure in physics is what defines existence. But we must be careful, not to drift too far from science into speculation. These ideas are possible, but not yet proven. They're maps we haven't followed, paths drawn in the sand of equations. Still, they teach us something, that black holes are not voids. They are the most active places in the universe, not just in gravity, but in thought. They force us to stretch the meaning of space, time, cause, and effect. They break our tools, and in doing so, they show us what new tools we might need. Black holes are not where science ends. They are where it must evolve. As we drift toward the center, the singularity seems closer. But so does something else, the question of what lies beyond. Because even if we don't survive the journey, even if the ship, the sensors, and the story all dissolve, the ideas remain. Black holes don't just consume matter, They produce questions, questions that outlive stars, that persist beyond collapse. And maybe, just maybe, that's the point, that falling into a black hole isn't just a physical event. It's a metaphor for science itself, a willingness to follow the questions past the horizon, past the safe answers, past even what we can see. So let's go further, not just deeper into the black hole, but deeper into the question itself. What is a black hole if we remove all metaphor, all fear, all cosmic drama? At its core, a black hole is just a solution to Einstein's equations. That's it. A set of math expressions that describe how space and time curve in the presence of extreme mass. The original solution came in 1916, just a year after Einstein published General Relativity. It was discovered by Karl Schwarzschild, a German physicist, who found that if you compress a mass into a small enough radius, the space-time around it folds in on itself. This creates a region from which nothing can escape. That radius, the distance from the center to the event horizon, is called the Schwarzschild radius. Every object has one, including you. If your body were compressed into a black hole, your Schwarzschild radius would be less than a trillionth of a nanometer. For Earth, it's about 9 millimeters. For the Sun, about 3 kilometers, which means you don't need infinite mass to create a black hole. You just need enough mass in a small enough space. And once that threshold is crossed, the collapse is irreversible. No force we know can stop it. This is why black holes are inevitable outcomes of stellar evolution. If a star is massive enough, gravity always wins in the end. But the idea didn't gain traction until decades later. In the early 20th century, the concept of a star collapsing into nothingness was too radical. Even Einstein himself was skeptical. He believed some unknown mechanism would prevent the formation of a singularity. But over time, as observations and theory progressed, it became clear. Black holes weren't just mathematical curiosities, they were real. In 1965, Roger Penrose proved a crucial theorem, that once a certain density is reached, collapse is inevitable. No matter how the star is shaped, no matter what pressure is inside, the outcome is a singularity hidden behind an event horizon. This was a turning point. It meant that black holes weren't rare. They were a natural endpoint for massive stars. And once that idea took hold, everything changed. We began to look for them. We found stars orbiting invisible companions. We detected gravitational waves from collisions between black holes. We saw high-energy jets blasting from the centers of galaxies, powered by accretion disks around supermassive black holes. And in 2019 we captured the shadow of one. The theories became images, the math became matter, and yet despite all of this progress, the singularity remains untouchable. We can describe the space around it. We can measure the effects of its gravity, but we can't see it. And this is where a new idea begins to emerge, that black holes are not objects, but boundaries, not things, but limits. Each one marks the edge of what we can know with current physics. And perhaps that's why they fascinate us so much, because they are, quite literally, where certainty stops. There is no experiment we can do inside a singularity, no observer we can interview, no data we can collect. And yet, we keep asking. We keep falling into the question, because even if we never find a final answer, the pursuit itself reshapes what we believe. It forces us to think beyond particles and forces, beyond coordinates and clocks. It asks us to question the nature of space itself. What does it mean for space to curve? Is it stretching, bending, folding? These are words we use to describe something more abstract, the geometry of the universe. General relativity tells us that mass tells space how to curve, and space tells mass how to move. But this curvature is not like a physical sheet. It's mathematical, conceptual, and yet its effects are real. We can measure the bending of starlight around a black hole. We can calculate the delay in time as signals pass through curved regions of space. And in extreme cases, like black holes, we can see space become so warped that it effectively traps itself. The event horizon is not a wall. It's a place where the slope of space becomes vertical, where all paths lead inward, where escape is no longer an option, not because of a force pulling you in, but because the very structure of space-time has changed. In this view, gravity is not a pull, but a fall, not an attraction, but a bending. When you orbit the Earth, you're not being held up by an invisible force. You're falling around the Earth continuously on a curved path through bent space, and inside a black hole, that fall becomes inescapable. Every direction leads inward. Every moment takes you closer to the singularity. It is not a choice. It is the shape of the universe in that region. And if this all feels dizzying, good. It should, because you are now standing at the edge of human knowledge. This is what it means to confront a black hole. Not to imagine a monster, but to face the boundary of our current understanding. And still, you're listening, still asking, still holding the question open. That, in itself, is a kind of bravery. We're not done. Because while black holes may be places where space ends, they may also be places where time begins again. And that possibility, that from collapse comes something new, is where we'll head next. So let's turn now toward something even stranger, the idea that inside a black hole, past the fall, beyond the singularity, something might begin again. Because if black holes are where the known rules stop working, they may also be where new rules begin. And some physicists believe that what lies beyond the singularity is not destruction, but birth, not an end, but a bridge. To explore this, we need to step gently into a realm of theory, not science fiction, but speculative physics, grounded in real equations. One such idea is that of the Einstein-Rosen bridge, more commonly known as a wormhole. The concept comes directly from Einstein's theory of general relativity. In the mathematics, it's possible for space-time to connect in such a way that two distant regions, or even two different universes, are joined by a tunnel. If a black hole exists at one end and a theoretical white hole exists at the other, matter might fall into one and emerge from the other. A white hole, in theory, is the opposite of a black hole. It expels everything, admits nothing, and exists as a kind of time-reversed version of collapse. But there's a catch. Wormholes, if they exist, are unstable. The tiniest disturbance could cause them to collapse. To remain open, they'd require something exotic, a material with negative energy density, something we've never observed in usable form. Still, the possibility remains. In fact, some physicists think that black holes are wormholes, or at least that their interiors might connect to something else. One idea, called the black hole cosmology model, proposes that every black hole could give rise to a new universe on the other side of the singularity. In this model, the Big Bang wasn't the beginning of everything, it was the other end of a black hole in a larger parent universe. We live in the expansion that emerged. The mathematics allows it. The logic is consistent, but we have no way to test it, at least not yet. And maybe we never will, because the nature of a black hole is to seal itself off. Once you fall in, you lose the ability to communicate with the outside. Your story becomes internal. And maybe, just maybe, the universe does the same. It buds off smaller realities from its black holes. It grows, not just in space, but in dimension. Each black hole, a seed. Each seed, a new Big Bang. And in that model, time doesn't stop at the singularity. It flips, it turns, it begins again. This is not fantasy. It is one of many serious attempts to reconcile what happens inside a black hole with what we know about our universe's origins. After all, the Big Bang itself, the point from which everything we see expanded, began as a singularity. That singularity was also a place where the laws of physics broke down. So maybe the singularity in a black hole is not so different from the one at the beginning of time. Maybe they are two sides of the same idea: collapse and expansion, inward and outward, death and rebirth. But what would that mean for you, the falling observer? Would you be torn apart before you reach the other side? Would your atoms reassemble in a new universe, unaware of where they came from? Or would your information, the pattern of your structure, the shape of your memory, become part of the new space-time fabric? We don't know, and maybe we never will. But to ask the question is to brush against the edge of something enormous, not just in physics, but in philosophy. Because if our universe was born from a black hole, then maybe black holes are not to be feared, but respected. Maybe they are part of the cycle. Maybe they are how the cosmos regenerates itself. You're still falling, still drifting inward. The ship has long since passed the horizon. Sensors are failing. Time is no longer moving as it once did. The shape of your thoughts begins to stretch, as space does. You feel the structure of your body, the idea of up and down, unravel. You are not disintegrating. You are dissolving into perspective, becoming one with the direction of gravity. And in the far distance, or perhaps the near future, lies the singularity. But now you no longer see it as an end. You see it as a turning point, a place where the inward curve flips outward again. A mirror, not a wall. The last thing you feel is the bending of time. Not violently, not with fear, but like a ribbon folding into itself. Not an explosion, not a crash, but a transformation so slow, so smooth, it's almost quiet, almost soft. Maybe black holes don't destroy. Maybe they edit, reorganize, rewrite, and maybe on the other side of that rewrite is a beginning you'll never remember, but one the universe will. Let's stay with that idea. The possibility that black holes are not the brutal erasers we once feared, but cosmic editors, sculpting matter, energy, even space itself into something new. Because if black holes truly end in singularities, and singularities give rise to new universes, then every collapse is also a kind of creation. But how do we even begin to make sense of such enormous claims? We do what science always does. We look for patterns. We look backward in time, toward the most famous singularity of all, the Big Bang. The moment, or perhaps the region, when our observable universe began to expand. At first glance, it seems the Big Bang and black holes are total opposites. One is an explosion outward, the other a collapse inward. One spreads energy, the other swallows it. But in the mathematics of general relativity, they share something profound. They're both solutions to the same equations. In both cases, space-time becomes extreme. Curvature becomes infinite. The known laws break down. The beginning of our universe may have been the interior of a black hole, not in our universe, but in another. Some theories even suggest that black holes and big bangs are part of a cosmic cycle, where universes give birth to new universes through black hole singularities. The universe could be not a single event, but a branching tree. One black hole, leading to a new space-time, each space-time generating its own stars, its own black holes, its own children. This is more than poetic. It's mathematically consistent with many theories of quantum gravity. Models like loop quantum cosmology, for instance, avoid singularities altogether. They propose that instead of infinite density, the collapsing core of a black hole reaches a point of maximum compression, then bounces outward into a new expansion. This is not a philosophical stretch. It's the attempt to bring together the sharp logic of relativity with the uncertain dance of quantum mechanics. In these models, the Big Bang wasn't the beginning. It was just the last bounce. And black holes? They are the next ones waiting to happen. And yet, despite all the elegance of these ideas, we remain outside looking in. We cannot test them directly. A traveler into a black hole could never send data back out. We are like ants trying to understand a volcano by watching shadows. And yet, we do not stop. We build better telescopes. We measure gravitational waves from merging black holes. We stare into the afterglow of the Big Bang, the cosmic microwave background, and search for clues. And all of it leads to one quiet truth. The universe is more connected than we ever imagined. The collapse of a star and the birth of a universe may be two faces of the same geometry. The singularity is not a location, it is a transition. And if that's true, then we, as observers, thinkers, wanderers, are part of that process. We are patterns inside a structure that folds, bends, and continues. Our atoms were forged in stars. Those stars ended in black holes, and maybe those black holes began new worlds. That's not metaphor, that's physics. Now let's ask a quieter, but equally profound question. If the inside of a black hole could become something new, a universe, a geometry, a rewrite, what happens to time itself in that process? Does it stop, reverse, loop? Time, after all, is not separate from space. It's part of the same fabric. And inside a black hole, time is twisted. We know this. Clocks slow near strong gravity. Light stretches into longer, redder wavelengths. And deep inside, past the event horizon, time flows toward the singularity like space. You cannot resist it. You cannot pause it. You cannot even define it in the same way. But if a singularity leads to another expansion, a Big Bang, then perhaps time begins again. Not in continuity, but in origin. A new arrow, a fresh direction. A universe where the laws of physics may look different, where time may move faster or slower, where matter is built from different rules. You, the observer, would never know. You would not survive the crossing, but your information, your structure, your atomic configuration might echo forward. Translated, rewritten, carried not as awareness, but as consequence. In this view, every black hole is a memory, and every universe is a response. Cause and effect, stretched across space-time, passed on through singularities. The cosmos becomes a dialogue, not a monologue, a lineage of transformations. And somewhere in that lineage, here we are, listening, asking, wondering what happens when the stars collapse, and what might happen after. So now we arrive at a point where black holes no longer feel like dead ends, but intersections. They are not singular finalities, but crossroads where geometry, gravity, and uncertainty collide. And yet, for all the imaginative roads we've followed, through rebirth, through wormholes, through cosmic bounce theories, we must now return to something more grounded. Because while we don't yet know what lies inside a black hole, we do know a great deal about what happens around one, and what we've seen is nothing short of astonishing. Surrounding many black holes, especially supermassive ones, are vast spirals of gas and dust called accretion disks. These disks form when matter, stars, clouds, even smaller black holes, wander too close and begin spiraling inward, caught by the black hole's gravity. But before the matter is consumed, it heats up, it compresses, it rubs against itself with unimaginable force. The temperatures rise into the millions, and in that moment, right before falling past the event horizon, it becomes one of the brightest things in the universe. Black holes themselves emit no light, but the material around them can outshine entire galaxies. That's why, paradoxically, the darkest objects in space are also surrounded by some of the brightest structures we've ever seen. These luminous engines are called quasars, and we've detected them at astonishing distances. Some quasars are so far away that the light we're seeing now began its journey when the universe was still in its infancy. That light has traveled for billions of years, crossing space and time to reach our telescopes, carrying the imprint of black holes that formed when the first galaxies were still assembling. That's the strange thing about looking into space. The farther we look, the deeper into the past we go. Black holes, which may represent the end of things, also serve as lanterns from the beginning. Their glow, not from themselves, but from the chaos around them, illuminates the early chapters of the cosmos. And, in recent years, we've seen something even more profound. Not light, but ripples in space-time itself. In 2015, scientists at LIGO detected gravitational waves for the first time. These are tiny distortions in the fabric of space-time caused by cataclysmic events like the collision of two black holes. When they merge, they send out waves, like ripples from a stone dropped in water, except these ripples travel at the speed of light, stretching and squeezing the space they move through, and those waves, though impossibly faint, reached Earth. Our instruments felt them, and in that moment, we weren't just seeing black holes, we were hearing them. Not in sound, but in vibration, in rhythm, in the very structure of the cosmos. The idea that two black holes collided over 1 billion years ago and that the memory of their union could still be passing through us today. It changes what we mean by observation. It tells us that the universe speaks in more ways than we ever imagined, and black holes, once thought to be mute and silent, are among its loudest voices. But what do those waves really tell us? They confirm what Einstein predicted. They confirm that black holes exist, that they merge, that they lose energy as radiation. But they also open the door to new questions. What if two black holes collide and form something we don't expect? What if the waves carry fingerprints of quantum structure? What if, within those rhythms, we find evidence of information, of entropy, of the physics beyond relativity? The search is just beginning, and the instruments are getting better. We now have LIGO, Virgo, Kagra, and soon LISA, a space-based gravitational wave observatory that will float millions of kilometers above Earth, listening for the quietest notes in the cosmic symphony. We are no longer just observers of light. We are now listeners of space-time. And black holes are becoming instruments through which the universe plays its deepest chords. But while the science expands, the mystery persists. The more we learn, the more the questions multiply. What is mass truly when space bends this much? What is time when it stops making sense inside an event horizon? What is reality when no two observers can agree on what just happened? These aren't abstract questions. They're central to everything we believe about existence. And black holes sit at the core of that belief, challenging, reshaping, asking us to reconsider what we thought we knew. So let me pause again, not to explain, but to connect. Where are you listening from? Right now, as we drift through these cosmic puzzles, where are your feet? Your eyes? What stars are above your roof? Drop your city in the comments below. I read everyone. It reminds me that even. Though we speak of things billions of light years away, the questions bring us closer, to each other, to the quiet, to the wonder. And if you're still listening, still asking, still curious, consider subscribing. You're part of a very gentle, very thoughtful group of people. People who don't need fast answers, just deep questions. Now, back to the edge. Black holes may teach us more about the universe than anything else. They are the extreme case of every law we've ever written. And when our laws break down, we are forced to look deeper, to rethink the fabric beneath it all. And if you ask a physicist where their curiosity lives, many will point here, at this collapse, this curve, this darkness that somehow glows. Let's now shift the lens just slightly, from what black holes do to what they mean. Because no matter how deep our equations go, no matter how detailed our models become, black holes always give us something more than just a physical structure. They offer a metaphor, one that sits quietly inside our understanding of the universe. In the laws of physics, black holes are defined by their simplicity. They erase detail, they hide complexity, they reduce stars, dust, gas, even light, to a handful of measurable quantities: mass, spin, and charge. This is known in physics as the no-hair theorem. The idea that once matter falls into a black hole, all other features are stripped away. No hair, no fingerprints, no distinguishing marks. The black hole doesn't remember what it consumed. From the outside, a black hole that formed from a supernova is identical to one formed from a collapsed alien spacecraft, so long as their mass, spin, and charge are the same. It's a chilling idea, in a way, that the universe can be so indifferent, so quiet, so clean, but it's also elegant, because in that simplicity we find the boundary between entropy and order. Black holes, according to physicist Jacob Bekenstein, have entropy, a measure of disorder, of hidden information. And Stephen Hawking later showed that a black hole's entropy is directly proportional to the area of its event horizon, not its volume. That was strange. Most objects, stars, planets, gas clouds, have entropy based on their contents. But black holes? Their entropy lies on their surface. That idea became the seed of the holographic principle, one of the most influential concepts in modern theoretical physics. It suggests that the contents of a region of space can be described by information stored on its boundary, like a 3D image encoded on a 2D surface. And if that's true for black holes, maybe it's true for everything. Maybe our universe, vast, dimensional, expanding, is actually a projection of information written on a distant surface. That's not fantasy. That's math. It comes from attempts to reconcile quantum mechanics and gravity, to find a theory of quantum gravity that works not just in the abstract, but at the edge of a singularity. And once again, black holes are the key. They are the testing ground, the crucible, the place where ideas either break or transform. We used to think of black holes as dead ends, points where matter disappeared. But now we see them as gateways to new physics, to new math, to a universe where surface and volume are the same, where entropy is area, where information is never truly lost, only hidden, scrambled, woven into the geometry of space-time. And so, the black hole becomes not a mystery, but a map of the universe's memory system. But how does that memory work? How is the information of a fallen star, its shape, temperature, chemical composition, stored on the event horizon? No one knows for sure. Some theories suggest quantum entanglement plays a role, that particles falling into the black hole become entangled with those on the outside, creating a web of correlations that preserve information even as it crosses the horizon. Others propose that space-time itself is emergent, that what we think of as distance, gravity, and curvature are just the behavior of information at scale. And the black hole? It's where those behaviors become visible. But we must be careful, because here theory and evidence diverge. The mathematics is compelling, but the experiments are not yet possible. We cannot test the inside of a black hole. We cannot read the data off its surface. And yet, gravitational wave observatories, quantum field theories, and string models all keep circling back to the same truth. The answers might live here, not in the quiet vacuum of flat space, but in the roaring silence of extreme collapse. The black hole, once feared, is now revered, not because we understand it, but because every step toward it makes us understand everything else more clearly. Let me ask you again, gently, where are you tonight? As we float together in this enormous question, where is your body? Where are your thoughts? Are you near the ocean, hearing its tide? Are you in the mountains, wrapped in wind? Drop your location in the comments. I read them not as data points, but as constellations, small lights on the map of wonder. And if you're still here, still curious, still unafraid of the dark, I invite you to subscribe. This is a channel for those who don't rush answers, who drift, who listen. Now, deeper still. Because here's the question that matters most. What do black holes tell us about ourselves? Not as scientists, but as sentient beings, as observers, as minds trying to understand the frame we live in. I think they remind us of humility, that even our best equations end somewhere, that knowledge, like light, has a horizon, and I think they remind us of persistence. That mystery is not a wall, it's a signal to keep moving, that even the darkest regions of space still shape the stars. And maybe, just maybe, black holes are not a threat to meaning, but an invitation to expand it. Because if the universe can store information on surfaces, perhaps memory, identity, and structure live longer than we think. Perhaps the universe remembers everything we've ever done, not in stories, but in curves, in entropy, in time. So now we've journeyed far, across the equations, the paradoxes, the burning disks, and event horizons. And yet the black hole remains in front of us, unchanged, still silent. That's part of its strange power. You can study it from every angle, model it on whiteboards, detect its shadow, feel its gravitational pulse across galaxies. And still, at the center, it gives you nothing. No image, no voice, just a region of space that says, softly but firmly, not here, not yet. And maybe that's exactly why we keep coming back to it, because black holes represent something rare, not just in physics, but in human thought. They are not about what we know, they are about what we cannot know, about the very limits of perception, the edges of reasoning, the walls of light. The black hole is a cosmic silence, and silence, as we know, does not mean absence. It means depth, it means potential, and that's what physicists chase. Not the black hole itself, but the edge it sits on, because whatever comes after the black hole, be it rebirth, erasure, or a deeper kind of logic, cannot be accessed directly. It can only be inferred by how the hole behaves, by what it does to space, by how it changes time. And this is how modern science works. We do not stand inside the mystery. We measure the shadows it casts. We trace the distortions it creates, and from those distortions we build a theory, a picture, a map made of absence. That's what black holes teach us, how to read the missing parts, how to look at the light around a thing and understand the thing that gives off none. That's what the Event Horizon Telescope did in 2019. It didn't take a picture of the black hole itself. It imaged the glow of matter orbiting it at near the speed of light. It stitched together data from telescopes across the globe to create a picture that confirmed decades of predictions. That ring of fire, with its dark center, wasn't proof of destruction. It was proof of understanding. And still, the center remained black, still unreachable, still asking us to wonder. And now, let's pause, as always, to return from theory to you. Where are you in the world right now? Where are you sitting? What time is it, as we speak of the universe folding in on itself? Drop your city, your coordinates, your place. And if you haven't yet subscribed, and you'd like to follow these journeys into the gentle unknown, I'd be honored to have you along. This isn't a channel for fast facts. It's for those who wonder slowly, who drift comfortably at the edges of certainty. And that's exactly what the black hole asks of us, to be okay with not knowing, to lean into a kind of humility that is not defeat, but invitation. Because what's truly strange is not that we can't see inside the black hole, it's that the black hole still shapes everything outside it. It still bends light, still influences stars, still guides the architecture of galaxies. In a way, black holes are like ideas, invisible yet inescapable, impossible to hold yet shaping everything around them. And like ideas, they evolve. They aren't static objects. They grow, they feed, they merge, they even evaporate, though slowly. Black holes change, and that too is important, because it tells us that even at the edge of physics, even at the border where laws break, change is still possible. The black hole may trap everything, but even it can't hold off entropy forever. Hawking radiation, though faint, is a reminder. Even silence ends. Even darkness fades. Over trillions of years, a black hole loses mass. Its temperature rises. Its emissions increase. Until, in the far future, long after the last star has gone out, it vanishes. What's left behind? That again, no one knows. Some say nothing. Some say a Planck-scale remnant, too small to detect, but containing all the information that was ever stored. Some say the black hole bursts, revealing the data in a final flash. We have no observations, no consensus, but again, the mystery is not the point. The questions are. Because every time we ask what happens next, we sharpen the edges of what we do know. We deepen the meaning of observation. We remind ourselves that science isn't just about facts, it's about limits. And what black holes give us is a place where those limits become visible, tangible, real. They show us the edge and dare us to lean closer. And maybe that's the most powerful thing they do. Not destroy, not erase, but point. Point toward the future of physics, toward the theories we haven't written yet, toward the tools we haven't built, toward a new kind of understanding, one that can hold space, time, quantum uncertainty, and gravity in a single shared language. We're not there yet, but every observation, every ring of fire, every ripple of gravitational waves brings us closer, and the black hole, silent as ever, simply waits. Not passively, but with purpose, as if it knows it is the question, as if it has always been. And now we reach the final descent, not into the black hole itself, because that journey, as we've seen, has no true endpoint, but into the heart of what this entire question has always been about. Because black holes in their terrifying silence do not just reshape the universe, they reshape us. They shift the way we think about space, time, matter, and memory. They ask us to let go of linear thinking, to imagine a place where distance folds, where time flows toward gravity, where light cannot escape, and yet meaning does. They invite us into a realm where math trembles, where geometry curls into itself, and where reality stops being something we can observe and becomes something we must imagine. Black holes are the ultimate scientific confrontation, the place where two of our most successful theories, general relativity and quantum mechanics, refuse to cooperate, where the smooth fabric of Einstein's space-time meets the jittery unpredictability of quantum particles, and neither gives in. The singularity is more than just a place of infinite density. It's a symbol of our unfinished work, a blinking cursor at the end of the universe, waiting for new equations, waiting for insight, waiting for us. And maybe that's why we keep returning to it, because the black hole doesn't just represent collapse, it represents potential. A singularity is not the death of science. It's a call for its evolution. And as our telescopes get sharper, our detectors more sensitive, and our minds more open, we move closer, not to solving the black hole, but to understanding the question it asks. What is space, really? What is time when it falls into gravity? What does it mean for something to exist if no one can see it? These are not just scientific questions. They are philosophical. They are human. Because in the end, the black hole reflects the very experience of living. We are born, we observe, we think, we remember, and then we pass into something we cannot explain. Life, too, has an event horizon, and whatever lies beyond it, whether silence, transformation, or something utterly unknowable, remains invisible to those still on the outside. That's what makes this journey universal. That's what connects you, sitting wherever you are, to the stars collapsing in distant galaxies. The same physics, the same gravity, the same curiosity. Black holes are not out there. They are part of the same fabric that runs through your bones, your breath, your heartbeat. They are reminders that even in a universe where some regions remain unseen, the effects are still felt. Light still bends, time still stretches, and minds still reach toward what they cannot grasp. And so, as we end this slow drift into the darkness, I ask you one final time, where are you right now? Tell me. Share your coordinates, your city, your tiny bright dot on this vast planet. Drop it in the comments. I read them all. Each one is like a star in a quiet galaxy, proof that curiosity doesn't need to be loud to be powerful. And if you've come all this way, all 12,000 words, all these orbits around the unseeable, I hope you'll consider subscribing. Not because you need answers, but because you're the kind of person who knows that asking the right questions is its own kind of light. Now, let me leave you with one last thought. When we talk about black holes, we're not just talking about physics. We're talking about the edge of knowledge, the edge of perception, the edge of what it means to be a conscious being in a silent, ancient, spinning cosmos. And that's not frightening. That's beautiful. Because it means that every time you wonder, every time you sit with a question too big to hold, you are practicing the very heart of science. You are standing at your own event horizon, peering in. And in that moment, you are just like the universe, mysterious, unfinished, full of gravity, and always, always moving towards something more.